Welcome to True Makers. This is TechTips. The tip of the day is find a thermal coefficient of an RTD element. So makers, why is it so important to have accurate temperature? Well, everything from smoking meat all the way to industrial furnace. If you don't have accurate temperature, you won't have a quality product at the end of your process. So today we're going to find the temperature coefficient of an RTD element, or a device to measure temperature. The temperature coefficient is a known change in resistance for different types of metals with a temperature change. The reason that's so important is it gives you a very accurate temperature measurement for a potential process or program, like a PID loop. The way we're going to do this is first I'm going to boil it and measure it, then I'm going to freeze it and measure it, then go look for all the error of all the measurement devices, including the RTD element. We'll apply this math, and then we'll have a result. Hey True Makers, let's move on to the instruments that I'm using for these experiments. So over here I've got a Fluke 117 True RMS digital multimeter, and as you can see it's a very accurate multimeter. I got these silicone test leads that go over to some alligator clips, and the reason I'm using alligator clips is because it makes it very easy for me to connect this to the RTD. Then the actual RTD itself is an Omega Platinum 100 ohm 3-wire, and its published temperature coefficient is a standard DIN with an alpha equal to 00385, and of course this is what we're testing. And then on the cold side we have a thermopro pin, and the part number for the pin is a TP19H. And the reason I want to use this one is because he can sense way below 0. On the hot side I'm also using thermopro, and the part number is a TP20S. And as you can see, this element makes it a lot easier for me to mount this to a pot that's boiling. So now on to experiment number 1, testing the RTD at boiling point or 100 degrees C. As you can see, we are boiling at this point, and the Fluke tells us we're at 138.7 ohms at 100 degrees C. So let's move on to experiment number 2, or testing the RTD at 0 degrees C or freezing point. So one problem I had to figure out was how to get stabilized temperature around freezing. And unfortunately, the air temperature around just ice is much cooler. So what I chose to do is use an ice water bath. And what we have right now is a 0.4 degrees Celsius, and our Fluke is telling us 100.7 ohms at 0.4 degrees Celsius, within less than 1/2 degree error. Before we get to the final result, I'd like to discuss accuracy and error real quick. We have some error in both the multimeter as well as the RTD, and we have some potential voltage drop across the wires. Also, we're 600 feet above sea level, so boiling point is close to 99.5 instead of 100 degrees C. So this chart shows you how some of these errors line up. So as you can see, this is the experiment at boiling point. And in dark red, you can see the target temperature as well as the target ohms. In the green beneath that, you can see the observed temperature and observed ohms. And all the way at the bottom, you can see a linear fit as well as quadratic fit, and I use this to align the temperature to the ohms that were observed. If you only look at the test lead deviation and the actual voltage drop of the wires of the RTD, we more than make up for the error. Of course, there's still error with the multimeter as well as the RTD and the fact that we're 600 feet above sea level. So this is an excellent result for experiment number 1. So the chart you're looking at now is for experiment number 2 at freezing point. And in dark blue, you see the target temp as well as the target ohms. In green beneath that, you'll see observed temperature and observed ohms. And what you'll notice is it appears as if we've come up with a nonlinear result compared to experiment number 1 because of the greater deviation. I'm still using the quadratic fit and linear fit in order to align my ohms with my temperature. And just like the first time, if we only use the test lead deviation error as well as the voltage drop in the RTD wires, we more than make up for the error. However, there would still be some potential error with the actual Fluke and the RTD, but regardless, we have a really good result here as well. So after running our experiments, we now know that all the devices are within the published accuracy and error. Hey True Makers, now for a final result. After running the experiments, we know both ohms for boiling point as well as freezing, and we know potential error across our measurement devices. So what you see now is an equation to determine the temperature coefficient for an RTD. And I've even added in the error for the measurement devices, as well as the fact that we're 600 feet above sea level. So, this Omega Platinum 100 ohm RTD, there's no question it has a standard DIN temperature coefficient with an alpha equal to 0.00385. It's confirmed. If you like our videos, please come subscribe to our YouTube channel, but there's just one more thing. You gotta join us again for another tech tip.